Hello everyone. In the last class, we started our discussion about predicate logic, which we found to be an extension from propositional logic, where propositional logic has certain insufficiency to express some of the constructs or arguments or statements in English. However, we have found that with the introduction of quantifiers, functional symbols, variables, and constants, we could eliminate that insufficiency in propositional logic and could encode much freely many of the statements and we call this logic as first order logic or predicate logic. To give a brief recap, we found out that there are certain quantifications and associations that we cannot express in propositional logic, and hence we started to introduce the predicate logic with new variables, constants, functional symbols, predicate symbols having Boolean truth values, connectors as well as existential and universal quantifiers. We have also seen in the previous lecture how to encode using propositional logic with the nested quantifiers and what is the meaning of for all there exist in case of multiple nestings of that. We have also seen the introduction of certain kind of functional symbols, by which in the last class we also saw that how we can encode that using the functional symbols inside the predicates. In today's class, we shall be mostly discussing about the formalisms in a more formal way, the syntax and the semantics and the rule-based deduction systems that we could invoke to derive whether a formula is valid or satisfiable. We will try to see one by one the notions and we will try to deduce through some examples that how we can derive from this predicate logic formulations. To start with, the concept of equivalence and implications, let us define that. So we say that two predicates, if you remember that the predicates have Boolean values, so we say that the predicate Px, for example, X is a passenger, X is a dancer, like that. The two predicates Px and Qx are said to be logically equivalent when for every particular value that variable can take within the universe, I can say that PA if and only if QA holds for every possible values like A, B, C, everything. So formally we write it as for all X, if X is of type P, logically equivalent to QX. So for all values Px is logically equivalent to Qx. Similarly, we can define the implication as a predicate Px is said to logically imply another predicate Qx when for each x equal to a in the universe, Pa imply Qa holds. It means that for each a which the value which x the value a which x can take, whenever Pa is true in that universe, I will get Qa to be true as well. So therefore we formally express it as for all x, Px logically imply using a thick right arrow Qx. Okay, so here we are introducing two new notations, which is thick both side arrow to imply logical equivalence and one-sided right-sided thick arrow to say some predicate logically imply other predicate. Let us try to see some of the rules based on these new equivalence and implication constructs. If you try to say that there exists X where the predicate Px and Qx both are true together, so if this is the case, the left side, there exists X, Px and Qx, then it means since both are true, so for that particular X or for that X that you have taken, Px is true, along with that Qx is true. So it will automatically imply that there exists X Px and there exists X Qx. So you could distribute this there exists X into Px and Qx provided it is conjuncted with an AND. However, the reverse side implication is not true. Because you see that if I say there exists x px and there exists x qx to be true, maybe that for x equal to a the first thing is true and for x equal to b the second thing is true. Now when I try to say for a same x both should hold, it is not the case. So therefore the red thing in the second bullet that I have pointed is not implying there exists x px and qx together. So it's an one-sided implication which holds, the other sided implication does not hold here. However, if you see there exists x px or qx, it means that for some x, px or qx, any one of them or both may be true. Which is similar as saying that there exists x px to be true or there exists x qx to be true. And see here the logical equivalence between them. So equivalence is nothing but logical implication from both sides. So if I have there exists x px or qx, then I can also conclude there exists x px or there exists x qx and vice versa. Because from the right side, it says that even if these two there exist x takes different values, but I need one of them when I make it at a or in the left side, I need one of them to be true. So if the right side is true, it will automatically imply the left side is true. Similar for the for all x with and. So this for all x can be distributed over and. It says that for all x, px and qx both are true. So to have both px and qx true for every x, then px and qx individually must be true for every x. So it is if and only if or logically imply in both directions. So it is logically equivalent that we distribute for all x over and. Coming to a last set of examples, if we try to distribute for all x over or, we may not distribute it and make it logically equivalent. However, there is one-sided implication still holds as the first two cases, as just like the first two cases. So what I say here is that for all x px or for all x qx, it means px and qx both holds for all x. So it means that if the first part holds or the second part holds. So if I make px or qx together, since first part or the second part has already holding here, so in the right side set of formula is also to be true. So whenever for all x px or for all x qx is true, then I can say for all x px or qx must be true. But now look at the reverse implication, which is shown in the last red statement. So when I say for all x px or qx, it means that for a particular x, px may be true, for another x, qx may be true. It does not guarantee that for every value of x, both px and qx should be true. To give you an example, let's say x can take the value a, b, c, d, so on. So let's say for x taking the value a, p of a is true but q of a is false. Then x is taking the value b, where p of b is false, q of b is true. So making this particular whole formula to be true. Now coming to the right formula, in the example just now I discussed, you cannot say because for all x equal to a, pa is true, x equal to b, pb is false. Therefore for all x, px is not true. And here also I get for x equal to a, that is qa is false, however x equal to b, qb is true. So therefore for all x, qx is also not true. So I got a particular valuations here where this part, the left part is true, however the right part I cannot satisfy. So this does not logically imply the right part. So therefore I can only see that there exist can be distributed over or, which can logically imply from both ends. For all can be distributed over and can logically imply from both ends. However, there exist can be distributed over and in one-sided and also for all with respect to or in one side, not in both direction That is why we cannot say both as logically equivalent in the first and the last cases. So let us now come to the primary semantics or fundamental syntax of the whole thing. So we have introduced certain thing called variables, constants, predicates and functions. Let us try to see one by one what does the semantics mean. You have already noticed that if I declare a predicate like pred x comma y, for example, goes x comma y, x goes to y. So pred x comma y and associate two variables, I can have before it for all x pred xy. Now if I do not quantify or use the quantifier for every variable, it means that I have a bound for x but I do not have any bound for y. So x here is a bounded variable, y here is a free variable. X is bounded by immediately nested quantifier, that is for all x here, y is free. Let us come to the second example where we say that for all x, predicate pxy and there exists z, predicate qxyz w. Here you can see that the for all x has the scope of everything inside it. So therefore the variable x within predicate p as well as the variable x within predicate q both are bounded by the for all x, this quantifier. However, the variables y in both these predicates are still free, so as the variable w in predicate q. But the variable z in predicate q is bound by the immediately nested quantifier there exists z. So x in both predicates are bounded by for all x, z in the predicate q is bounded by there exists z, y in both predicates are free, w in the predicate q is free. Now we can also have a scenario that a variable in one predicate is bounded but in the other predicate it may be free. So let us see the last example formula that we have constructed, that for all x pxy and there exists y, there exists z, qxyz w. As you can see that both the x in predicate p as well as q are bounded by immediate nested quantifier for all x. The first predicate pxy, the variable y inside it is not bounded by anyone. However, the variable y inside the predicate qxyzw is bound by there exists y, that is its immediately nested quantifier. So as the variable z in the predicate q is also bound. And like the previous case, variable w is again free. So here we have variable x to be free for both the predicates, variable y to be free only for p predicate p but not free for predicate q, which is bound by the quantifier there exists y. Variable w for predicate q is free, variable z is bound by there exists z. So this is the concept of free and bound variables in predicate logic, and there are scopes in which these boundaries of the variables are defined, or some variables is bound within its scope. So what is the reason behind proposing such kind of a construct is that, let us take the last example. When we say there exists y, then I could take a particular y for which I could replace, let's say, y equal to p, or y equal to, let's say, y equal to m. And I could replace this y by m, but I cannot replace the y in the predicate pxy, because that y is free. When I try to bind the other y in q, it is bounded by there exists y, not the first y is bounded. So when we try to deduce or produce the deduction rule with respect to these quantifiers and try to take an instance in case of there exists y, then the scope of these variables are very much important to reason about things. So in a nutshell, what we found out in terms of the semantics, that when we move from the propositional logic to the predicate logic, we found that in propositional logic we have our propositions taking as truth or failure values, Whereas in predicate logic, we extended it in terms of predicate symbols taking the true or false values. Therefore, the Boolean outcome here has been dictated by the predicates. In propositions, we could have constant symbols, or the constant symbols can get extended to function symbols which can produce values. So this particular extension makes us, along with the quantification obviously, makes us to a little bit higher order logic to express many things which we cannot express using propositional logic. However, you could also see the fact that quantification is eligible only for variables to be quantified. It does not allow you for the symbols or the name of the predicates or the name of the functions to be quantified. For example, you cannot say, if we define, let's say px is your predicate, let's say x is a passenger, so pass x as we have defined, I cannot say there exists p. So this is not in the particular scope or in the syllabus of predicate logic anymore. So we cannot quantify the name or the symbols, predicate symbols and functional symbols. Similarly, when we say greater than age of x is greater than age of y, where age is my functional symbol, I cannot say there exists age. I can give for all x, for all y, which are the variables participating inside it, but I cannot take the name of the function symbols and the predicate symbols as quantifications. So this is one thing that is restricted in this first order or predicate logic. With this premise, we can come to the formal terminology and the semantics of predicate logic. The constant symbols are, let's say M, N, O, P, these are the constant symbols. We have variables inside it. We have function symbols with different sets of arguments, but finite set of arguments as of we have defined. We have predicate symbols, which gives us true false values or Boolean values, and it can also take variables as arguments. Remember that the predicate symbol can also take function symbols as its arguments, as we have seen in the greater than function taking age of x and y as arguments. We have Boolean connectors as we have seen in propositional logic, and we have quantifiers like for all and there exist. We define something called as a term, that my variable as well as my constant symbols are terms. So x, y, z, m, n, o, p are terms. Now, if ti is a term and f with k parameters is a functional symbol, f which can take k number of parameters is my functional symbol, then f with those terms, k number of terms, together forms a term. So what we are trying, so let me tell you what we are trying to reach here. In all the previous examples, we have denoted or encoded the arguments in terms of a formula. And we have seen that the predicates can take inside it as arguments functions. So there could be nestings, in the quantifications. So can we somehow recursively define a formula? That is our ultimate goal. That what is the basic or what is the fundamental nomenclature through which we could represent the semantics of a formula. Here we go. We say that a formula, or a well-formed formula to be more precise, we will denote everywhere the formula as the well-formed formula, is recursively defined as, when we say a proposition itself is a well-formed formula. If ti are the terms and p is a predicate which can take k number of arguments, then p of those terms is a well-formed formula too. Remember that these terms are defined as variables, constant symbols and functions, and as you can see that predicate can take variables, constant symbols like dancer Anushka. So Anushka is a constant symbol, dancer x is a predicate, so it can take that. So that is a well-formed formula. If f1 and f2 are well-formed formulas, so all the Boolean compositions of it, not of f1 and F2, F1 or F2, F1 implies F2, all are well-formed formulas. If Px and also there are more arguments is a predicate symbol where the meaning of x, why I put here x is the fact that I want to indicate that x is a free variable in this predicate. Then we can bound that by for all x p, that predicate px dot dot dot, and there exists x that predicate px dot dot dot. These forms again the well-formed formulas. So therefore we can say that there are two kinds of recursive constructs that we can define. One is term in terms of variables and constants participating inside the functions. And finally our formula or well-formed formula, to be more precise, which is propositions itself, predicates taking terms, two well-formed formulas which are conjuncted using Boolean connectives, a predicate with a free variable bounded by for all x or there exists x. This is the recursive definition of the formula, and all the formulas that we have encoded or deduced in our previous examples follow either of any set of rules that are defined recursively here. So this is the formal semantics or the terminology for the predicate logic, and over this terminology we define the whole predicate logic in a formal manner. Now with these definitions we could also now come that how do we interpret the values that we say that the function can take any value which can be non-Boolean. How do we say that the predicate can take the outcome of the predicate could be true or false? So what is the meaning of that? As you can see that a variable or a constant can take certain values. So that means there is a domain from where the set of elements or values are chosen in every interpretation, unlike the interpretations in propositional logic where we say that every variable can take true or false value. Here every variable as well as every constant can have certain valuations from a set of elements which we call as a domain. Now when we try to interpret a function, it means that this function will take certain arguments. Here there are n arguments and it will produce a value. So let's say the value it produces are from the set of elements of domain D, then it just defines a mapping from these products of these domains. So all possible combination of values of this domain. For example, if we say that we will define a functional symbol called sum xy, denoting that the sum of x and y, x plus y. So this is a function which will, let's say if x and y has the domain of integer values, so this will produce as an outcome an integer value. So it will map from one integer that is characterized by x and every other integer that is characterized by y and produce a new integer which will be the sum. So this means that every possible valuations of x can be added with every possible valuation of y to form a particular domain. Two things to note here. One is the fact that we have the variables participating in the functions and the predicates can be from a domain, and also may be the case that the domain is infinite, as in this case for the integers the sum of the integer, if we get an integer, that is also infinite. So the domain may not be always finite. So here the interpretations of the domain is not as straightforward, because in propositional logic, if we used, let's say, n propositions, then we have 2 to the power n number of possible combinations or truth table entries, which we call as interpretations. So now our question is that how can we deduce rules or formulas to derive a certain outcome where our set of values that it may take is an infinite. Similarly, in the same vein, we can declare predicates as a mapping which can take values from the domains of its arguments and map it to true or false, because predicates will outcome a Boolean value. So for example, if we say x is greater than y, it says that gtxy, it denotes it by gtxy, where x and y can be two values. It can also come as an outcome of a function, as we have seen, age of some person and age of another person. So that outcome of a function may be, let's say, sum of two values is greater than sum of other two values. So that is the outcome from domain D, which is integer. So it takes two integers and returns as a result either the first integer is greater than the second, then it returns true, or it returns false. So therefore, under such kind of a domain adaptation of we can interpret predicate functions and thereby our well-formed formulas as a whole, and can say how we will deduce it. With that, we will try to say that what are the meaning of how do we inference the outcome of a formula? What is the formal interpretation of that? This is basically the similar as we have derived in propositional logic, that we have valid, invalid and satisfiable, unsatisfiable interpretations of a formula. So here a formula is valid if it is true for all interpretations. Now, interpretations here could be infinite, as I already pointed out, but we need to reason about or justify that a formula is only valid if it is true for all interpretations. A formula is invalid if it is false in at least one interpretation. That is just the negation of the valid. What we need for validity to hold is just the negation when we have invalid case. A formula is satisfiable whenever it is true under at least one interpretation. A formula is unsatisfiable if it is false for every interpretations that we can perceive. So these are the sets of interpretation and inferencing rules over the terminologies that we have defined. Let us now try to deduce over some examples using this kind of interpretations and rules. We will first try to see few examples where we will apply some deduction rules as we have done in propositional logic, but here in a different sense because the domain could be infinite here. So we will try to see how we could conclude. So if you remember our first example in this predicate logic class, we say that wherever Ankush goes, so his pet dog also goes there. Ankush goes to school, you have to conclude that the dog also goes to school. So your query here is F1 and F2 implies G, this particular formula is valid or not. Here you can see I have a variable x which says for all x, wherever Ankush goes, so does the dog. Now let's say the domain of variable x, that is the possible element of domain D that the x can take, maybe school, ground or playground, library, etc. That means the places where a person can go are the domain that x represent. So here, since the formula 1 says that for all x, so Ankush can go to anywhere in this domain. So I can take x equal to school and replace in this formula F1, then also this formula should remain true. So when I replace it, it becomes F1 dash, it says goes Ankush school, imply goes dog school, which means that if Ankush goes to school, then his pet dog also goes to school. It is indeed an obvious implication from the previous one because previous one is unrestricted. It says everywhere Ankush can go. Now this eases our job a little bit because now along with these two F1 dash and F2, I can easily imply G because now I could see that these formula are just treated as propositional logic formula where I could directly apply the certain kind of modus ponens or modus tollens, all the laws of basic propositions or Boolean combinations, and to deduce a goal. It says goes Ankush school imply goes dog school. Goes Ankush school is true. So therefore applying modus ponens, we get goes dog to school is true. So therefore dog to school is our outcome, which is our G. So therefore it implies finally that F1 and F2 is G, because F1 is much relaxed. It says for all X Ankush X. But we have taken one particular instance that is school and it satisfies our particular query. So it is indeed, we can say that F1 and F2 is implying G to be valid. Let us take the second example, that no contractor is dependable, or in other sense for all contractors they are not dependable, which is encoded as F1. Some engineers are contractors, which is encoded as F2. So there exists X, which is an engineer as well as contractor. Then I have to deduce, or I have to finally reason about whether some engineers are not dependable. So the query is that if F1 and F2 implies G is valid or not. Here also, let us try to figure out that since it has been written that, look at the second formula, that there exists X, so some engineers are contractor. And as per the logical intent of the formula, I want to say there are some engineers obviously in this group from where I represent there exists X. So from that group, let's say A is an engineer from that group who is a contractor as well. So therefore, if I say X equal to A, then the second formula translates to engineer A and contractor A. Now if you look at the first formula is more generic because it does not have any restriction of any person or any people. So it say for everyone, if he is a contractor, he or she is a contractor, then he or she is not dependable. So therefore, if that person is A, then also this formula is true. So I can change, or I can rewrite F1 as F1 dash with a particular instance A as contractor A implies not dependable A. So what essentially I have done by choosing a particular instance for Formula 1 and Formula 2, instead having a variable or having this quantification of sum every, I have pointed it in terms of proposition alike predicates which now say true or false value for that particular person. Now the goal asks me that can I have such a person who is engineer and not dependable? Now if I can prove that for A this goal happens, then I am done, because I need only one person such that this goal engineer X and not dependable X to be true. There exists X, so at least one person should be there. So from the F1 dash and F2 dash that I just make out, if I can prove engineer A and not dependable A, then my job is done. If we have understood this particular extension of deduction, then the rest thing is very straightforward, because now we want to reason about whether F1 dash and F2 dash together implies G dash or not. It is indeed the case, because if you take F1 dash and F2 dash, it says contractor A implies not dependable A, and it says A is engineer as well as contractor. Therefore, in the first formula, this left side part is true. So it will imply obviously true modus ponens that not dependable A is true. Now if you take this not dependable A along with F2 dash, which says engineer A and contractor A as well as not dependable A, so obviously engineer A and not dependable A should be true. So therefore I got a person A where this formula holds, which means that there exists X, engineer X and not dependable X holds. So from F1 and F2 I could derive G, and hence F1 and F2 implies G. This whole formula is valid. Now, in the previous examples, we have seen some ad hoc basis. We have trying to deduce certain kind of outcomes and thereby trying to prove the validity or satisfiability of a set of arguments. Let us try to formalize this a little bit. So here comes certain inference and deduction rules, are very elementary sets of rules, because many of the rules we could derive from that. So there are in particular two types of basic rules that we will follow. One is called the rule of universal specification, which says that if for all x px is true, so if px is a predicate and for all x px is true, then pa is true for each element a from the domain of x in the universe. If you look at the last example we have done in the both examples for the formula f1, we have chosen an a and replaced that for all x with x equal to a, because since for all x holds, so for a particular value of that x within the domain also holds. So this is the first rule. The second rule is also says that if there exists x is true, then pa is true for at least one element a for the domain of x, which we use in the later case, that is in example 2, when we encoded f2 with x equal to a. So there exists some a where this holds, we can argue. Whereas for an arbitrarily chosen x, we can argue that the first thing is valid. So therefore using these base two rules, we can have certain derived rules as well. So you can see that if I have for all x, predicate px imply predicate qx, and I say that predicate p holds over a, so pa is true. Since for all x is nesting this, so that means for the value x equal to a, this whole thing should be true. So for the value x equal to a, if I substitute here, so pa should imply qa. Along with the pa, with that we can apply modus ponens and can derive qa. The second propositions, the second sets of arguments says that for all x px implies qx, and I say not qa. If x is a is from the domain of x, then for all x, if you substitute here by a, so pa implies qa should be valid. And once this is valid and we have not of qa, then obviously using modus tollens, we can say that not of pa is true. So these are set of derived rules which comes from the basic formulations of universal specification. Here if I say for all x, px or qx implies not of rx. So if I say Ra, where a belongs to the domain of x, what does it mean? That since for all x this above formula is true, so if I say R of a, that means if R of a happens, so not of R of a is false. So to have the above formula as a whole to be true, I need PA or QA must be false. So since PA or QA must be false, therefore not PA as well as not QA should be true. So it implies not PA. So this is just the derived rules which we could reason about manually by ourselves, but the fundamental principle remains here that if for all x is true, then for each element from the domain of x I could substitute here and could eliminate the universal specification, universal quantifier. The rule of universal generalization says that if for all x px is true, then PC is true for an arbitrarily chosen C from the domain X. This is just like saying that X can take certain values from a set of domains, where C can be any value. C can be capital A, C can be capital B, where A, B, C, let's say these are in the domain of X. So when we say that, if we can take arbitrarily chosen value, then we can eliminate this universal quantifier provided that your C is an arbitrary entity from that domain. Let us try to reason about how it simplifies or derives the other rules. Our basic goal is to have such kind of a base rule is that if we can eliminate the universal or existential quantifier, then it just acts like propositional logic, because we have predicates and Boolean connectors over the predicates to define the predicate logic. Now, if we eliminate the universal and existential quantifier, it just becomes a set of Boolean rules or propositional rules that we have to reason about. That's why in the previous case we can use modus ponens and modus tollens. This case also we will see how we can use universal syllogism. It says for all x, px imply qx, for all x, qx imply rx. So therefore, if I could substitute for any arbitrarily chosen c, that c could be anything in the domain of x. I could say pc implies qc, as well as for any arbitrarily chosen c from the domain of x, I could also say qc implies rc. Now you see that if whenever I eliminated this universal quantification, then pc implies qc and qc implies rc together say me that for an arbitrarily chosen c, I can say pc implies rc, which is universal syllogism in propositional sense. So for an arbitrarily chosen c, if this pc implies rc holds, so I can take back again, put back the universal quantifier and say for all x, px implies rx holds. Similarly, in this case, we can say that for all x, we have px or qx, and we also say for all x, we have not px and qx implies rx. So how can we reason about that? What happens if for all x not rx happens? So let us take x as arbitrarily chosen element c from domain D. So therefore, the second formula for all x not px and qx implies rx translates to not pc and qc implies rc. So when I say that not rc is valid, therefore this antecedent, the part before the implication, should be false, which means px or not qx to be true, applying De Morgan's law with having the false outcome from this negation of the whole thing. Applying De Morgan, we get px or not qx. Now the first premise says as px or qx. Here we are getting px or not qx. So rather pc or not qc if we arbitrarily choose c and eliminate the existential quantifier. So it says not rc implies pc for arbitrarily chosen c. So we can again put back the universal quantifier and get this result. This way I have shown you very few sets of derived rules, but as per the statements and the arguments that you construct, you can already formulate such kind of derived rules, or you can formulate new derived rules from these basic premises, that is universal specification and universal generalization, to eliminate the quantifiers and to bring it back depending upon the final arbitrarily chosen or existential entity wise, and can get the final results and or the deduction rules. So this is in a nutshell how we go about the deducing the predicate logic formulas in a formal way. So we will try to see more of these in tutorials, and we will try to derive certain kind of objectives from a set of arguments. Having said all of this, predicate logic is not flawless as well. So as we have already discussed about the insufficiency of propositional logic, so predicate logic is also not sufficient to express everything in this world. The only good part of predicate logic is that predicate logic can model any computable function. So anything that you could compute using your computer or in any computing machine, that can be expressed as a specification or logically using predicate logic and can be automatically reasoned out. Now there could be certain ways where we want to quantify symbols such as predicate symbols and function symbols that we are not allowed in, that is actually not allowed in predicate logic. For example, look at this formula. It says for all p, that predicate p with constant 0, and for all x, px implies this. So this somehow we do not write predicate formulas like this, right? Because we have said this is incorrect in terms of predicate logic. But this formula is a higher order formula where we also allow to quantify certain symbols, and we allow to quantify functions and predicates as for all and there exist. By the way, I left this is an exercise to guess what this formula expresses. A little bit of hint I have given. It's a very well known and popular mathematical theorem that we are expressing it here. But what this expresses, I leave it to you to think about. Similarly, there are extensions of predicate logics which we call as temporal logics, which is primarily used to define and or specify program behaviors or the circuit level behaviors. All we are doing in predicate and propositional logic is to relate some events or some arguments in a particular world which are not connected with time. It's just what is happening now. Temporal logics, on the other hand, in addition to these, can also specify something which happens in future, something which can happen in all time, something which can happen in immediately next time. So it allows us with certain new types of logical constructs to relate two different universes evolving over in different time. To give you a better understanding with an example, you can always see that in a circuit, suppose you give an input, you get a response after certain time. Now, obviously, if you want to verify whether giving a particular input gives you a particular output after certain time, how do you express that in terms of a logic? So, temporal logic comes in rescue for those kinds of specifications. Finally, what you could say that there are certain specifications which we call as unsolvable, which cannot be expressed as well in predicate logic as well. So let us have this interesting paradox that can we express using predicate logic these following statements? The barber saves all those who do not save themselves. Does the barber saves himself? So look at this particular set of statements that the barber saves everyone who do not save them. So now the question is, who saves the barber? So let's say there is a single barber in the town. This particular statement I can easily encode using our existing propositional or predicate logic. But those and only those who do not save themselves are saved by the barber. This creates a confusion that who saves the barber. If you say that the barber himself saves the barber, now this means that this will actually falsify the statement that the people who do not save themselves go to the barber. So if the barber himself saves his purpose, then this statement is false, because if you cannot save, then you go to the barber is false. On the other hand, if you say that someone else saves the barber, that contradicts the first statement, which means that there is a single barber in the town. So this is a paradox which you cannot express, because these statements and the outcomes that we want to do comes as a contradictory sets of arguments, and we say that this is undecidable or unsolvable specifications which the logical entities cannot encode with. So with that, we come to a conclusion of predicate logic, where we have learned that how to use quantifiers, how to use functional symbols, predicates, and the variables in proper way to formulate certain arguments. We have also seen how to reason about those using certain deduction rules, primarily the existential and universal generalization and specification process. We have also seen that a well-formed formula can be recursively defined using its terms, and which are the functions and the predicates. We have also seen there are certain limitations of predicate logic which other higher order or other logics tries to address, but there are set of functions which are not computable, which cannot be expressed using predicate logic or others, because that gives us certain kind of undecidable events or the set of events in nature. And that's why predicate logic is proven to only express all the computable functions, not beyond that. Thank you.